Hello everyone, welcome to the e-learning program of K.T.H.M. College Nasik. I am Dr.M.K.Deore from Department of Physics, K.T.H.M. College Nasik. Students, in this lecture, I am going to discuss about the fifth unit, the experimental methods of the X-ray diffraction, in which we are going to see the Laue method and the rotating crystal method. And the sixth unit is the de-Basser method. It is also known as the powder method. Students, in the first lecture and the second lecture of this chapter, I have already discussed about what do you mean by the X-ray crystallography and how the X-ray get diffracted from the crystalline material. Students, I want to revise it again about the X-ray crystallography and the X-ray diffraction. The X-ray crystallography is the experimental science determining the atomic and the molecular structure of a crystal, in which when a beam of the incident X-ray incident on a crystalline structure, they diffract into the many specific directions. Now we have seen in the Bragg's diffraction condition or in Bragg's diffraction law, when the X-ray incident on the crystalline structure, they diffract into the many specific directions. And by measuring the angles and the intensity of these diffracted beams, we can produce a three-dimensional picture of the density of the electrons within the crystal. And from this electron density, the mean position of the atoms in the crystal can be determined, as well as their chemical bonds, their crystallographic disorder, and the various other informations such as the average grain size, strain, and the crystal defects can be determined with the help of X-ray diffraction. So, the X-ray diffraction is a very important tool in the study of the crystalline structure of the different materials. Students, to study the X-ray diffraction from the crystalline material, we use the X-ray diffractometer. Now this is the schematic diagram of the X-ray diffractometer, and the basic elements of the X-ray diffractometers are the X-ray tube. Now it produces the X-ray of the different wavelength. Now then these X-ray will be collected through the collimator, and if you want a monochromatic X-ray, then you need it to pass through a filter that is also known as the monochromator, having a single wavelength. This monochromatic X-ray will be incident on a crystalline sample which is held by a sample holder. Then the X-ray will be get diffracted from this crystalline sample, and that diffracted X-ray will be detected by using the detectors. Now there are the different types of detectors are used. The generally scintillation counter and the gas field type of the detectors are used here. Nowadays there are the varieties of models of the X-ray diffractometers are available. Now this is one of the model of the X-ray diffractometer. Now then, for the study of X-ray diffraction, we need the monochromatic X-ray, then such a X-ray source can be obtained from the different types of target materials. Now in the discovery of X-ray, you very well known about how the X-ray get produced. We know that when a beam of the electron incident on the any target metal, then it produces the X-rays of the different wavelength. Now there are the varieties of the metal targets are used in the production of the X-rays. Now generally the molybdenum target which produces the K alpha radiation having the frequency having the wavelength 0.71 angstrom unit. If we use the copper, then it produces the 1.54. It produces the X-ray having the wavelength 1.54 angstrom unit. Now in this way the cobalt, the iron or that the chromium are the target material used in the production of the X-ray, produces the X-ray of the different wavelength. Now but generally the high intensity nearly the monochromatic K alpha X-rays can be used as a radiation source for the X-ray diffraction studies, and generally the copper target metal produces the K alpha radiations having the wavelength 1.54 angstrom units are used in the X-ray diffractometer. Now there are the different applications of the XRD. The X-ray diffraction, or you can say that simply the XRD, is a very powerful non-destructive technique used for the characterization of the crystalline materials. Now then there are the different applications of the XRD, or why we use the XRD. Now it is used for the differentiations between the crystalline and the amorphous material. It is used for the determination of the structure of the crystalline materials. It is used for the determination of the electron distributions within the atoms and throughout the unit cell also. The determination of the orientation of the single crystal, the determination of the structure of the polygrain materials. It provides the information about the structure, its phases, preferred crystal orientations, and also the other structural parameters such as the average grain size, the strain, and the crystal defects. So nowadays XRD is a very important tool in the study of the crystalline properties of the different materials. Students, we are going to see about the experimental X-ray diffraction methods. There are the three X-ray diffraction methods are available. The first one is the Laue method, second one is the rotating crystal method, and third one is the powder method. The Laue method and the rotating crystal method are used only for the single crystalline material, while the powder method is used for the polycrystalline type of the materials. Now we are going to see in details about these three types of the methods. The first one is the Laue method. The Max von Laue, a German physicist who received the Nobel Prize in Physics in 1914, for his discovery of the diffraction of the X-rays by the crystal. The Laue performed a very simple experiment of the X-ray diffraction from the crystalline material, and for his experiment of the X-ray diffraction, he received the Nobel Prize in Physics in 1940. Basically, the Laue method is used for the determination of the orientation of a single crystal and to study the symmetry of a single crystal. Now, this is the schematic diagram of a Laue's experiment. Now, it consists of the X-ray tube, the single crystal, and the photographic plate. In Laue's experiment, he used a polychromatic X-ray radiations having the wavelength varied from 0.2 to the 2 angstrom unit. This polychromatic X-ray will be incident on the single crystalline material, which is the stationary. So the glancing angle is fixed. The X-ray will be get diffracted from the crystalline material, and this diffracted X-ray will be incident on the photographic plate. We know that we have seen in the Bragg's diffraction law, when the incident X-ray incident on the crystalline material, and when it satisfies the Bragg's condition 2d sin theta is equal to the n lambda, then the rays will be get diffracted. Otherwise, if the incident ray will not satisfy this condition, then it will be not diffracted from the crystalline material. Now, in case of that, the single crystalline material, it consists of a set of the parallel plates, and from each set of the plate, there is the diffraction of the particular wavelength of the incident radiation, and it satisfies the Bragg's law, in which the glancing angle theta and the interplanar spacing d are the constant. Now here, due to the varied wavelength of the incident radiation, it satisfies the Bragg's condition and it get diffracted from the single crystalline material which having the number of the set of the parallel planes. Now we can see the diffraction pattern on this photographic plate. This diffraction pattern is the stereoscopic projection of the reciprocal lattice. Every point on this diffraction pattern represent the reciprocal lattice of the crystalline material. Now here, the wavelength is varied. Therefore, there are the several wavelengths can be reflected in the different orders from the same set of the plates. And due to that, with the different orders of the reflections superimposed on the same spot in the film, and it will be the difficult in the crystal structure for the determination by the spot intensity. And hence, this difficulty overcome by the another type of the method is known as the rotating crystal methods. So we are going to see then about the rotating crystal type of the method. The rotating type of the crystal method is used for the determination of the shape and the size of the unit cell, as well as the arrangement of the atoms inside the cell and the lattice constants. Now in case of that, the Laue method, we have seen that the Laue method is useful for the determination of a orientation of a single crystalline material and also to study the symmetry of the crystalline material. But now in case of the rotating crystal method, it is used to determine the shape and the size of the unit cell, as well as the arrangement of the atoms inside the cell, and also for the determination of a lattice constants. The rotating crystal method consists the basic element in which there is the X-ray tube which produces the polychromatic type of the X-rays. Now in case of that, the rotating crystal method, it required the monochromatic type of the X-ray, hence we need the filter. When the polychromatic X-ray will be passing through the filter, then it produces the monochromatic X-ray. Then this is the cylindrical holder which having the two pinholes through which the X-ray will be the enter from this side of the pinhole, and from this side of the pinhole the X-ray will be the loose. And also a photographic plate placed around inside the cylindrical holder. And the single crystal is mounted on the tip of the rotating spindle. Now here this is the specimen or the sample which is fixed on this rotating spindle. The size of the sample is, it should be not greater than 1 millimeter. Now here the monochromatic X-ray beam will be incident on the rotating crystal, which is rotated about the fixed axis. Hence now in this case here, due to the variation in the angle theta, it brings the different atomic planes into the position for the reflection which satisfies the Bragg's condition, and each producing the spot on the film. So now in this case also, when the incident X-ray satisfies the Bragg's diffraction condition 2d sin theta is equal to the n lambda, then it will be get diffracted. Now here the incident X-ray is the monochromatic, but the crystal is rotating and there is the change in the angle theta. Due to that, the changing position of the crystalline planes it satisfies the Bragg's diffraction condition, and the diffracted rays will be the incident on the photographic plate, which is held in a cylindrical hold. Now in this rotating crystal method, the beam is diffracted from a given crystal plane whenever the value of the glancing angle theta satisfies the Bragg's diffraction condition. Now in this rotating crystal method, the value of the glancing angle theta changes and it satisfies the Bragg's diffraction condition 2d sin theta is equal to the n lambda, because in this method the value of the lambda and the interplanar spacing d is constant, but due to the change in the value of the theta, it satisfies the Bragg's diffraction condition, and hence the incident X-ray diffracted from the single crystalline material. But the diffraction of the X-ray from the single crystalline material depends upon the position of the planes of a single crystalline material. When the diffracted beam from all planes parallel to the vertical rotation axis will be lie in the horizontal plane. Now that means when the crystalline planes which are parallel to this vertical rotation axis, then the diffracted X-rays will be incident on the photographic plate on this horizontal plane. While the planes with the other orientations the beam will be get diffracted above and below of the horizontal plane. Therefore, for a given value of the lambda, and by knowing the value of the theta, we can determine the interplanar spacing d by using the Bragg's law. that is the 2d sin theta is equal to the n lambda. And also the lattice constant can be determined with the help of this formula. D is equal to the a divided by the under root h square plus k square plus l square. That means the value of a lattice constant and the interplanar spacing corresponding to the planes having the Miller indices HKL can be determined with the help of rotating crystal methods.